Okay. So today is the last lecture of Ben Davison lecture series, the M seminar, and cohomological DT theory and nonabelian Hodge theory for stacks. Finally, the title of all lectures appeared on the slide. Okay, Ben, please.
Okay, thank you very much for the introduction. Thank you very much for the invitation and for your patience while we wait for the final component of this lecture to appear, which is indeed the nonabelian Hodge theory. Yeah, in this talk, I'm going to talk much more about nonabelian Hodge theory and about the P equals W conjecture of Deccartallo, Hausmann, Migliorini, and how to extend all of this to stacks. So stacks of Higgs bundles versus stacks of representations of the fundamental group of a Riemann surface. Now it will turn out that a crucial role in all of this is played by a recent result, which is the decomposition theorem for stacks of objects in 2CY categories. So I'll explain this theorem and I'll explain a few components of the proof. And the main component really is the proof of the analogous result for the category of representations of a pre-projective algebra, which is the content of the second talk. Okay, so let's crack on. So just a reminder, I mean, these first two slides are going to be almost carbon copies of the slides we've seen before, of the decomposition theorem. So we let X be a projective morphism of complex algebraic varieties. Just to remind you of my convention throughout these talks, that QX var is the constant sheaf on X shifted so that it's perverse. Then the derived direct image along P is of the constant sheaf is a split complex, meaning that it's isomorphic to its total cohomology. And moreover, each of the cohomology sheaves is semi-simple. And if X is singular, then the theorem needs to be modified slightly, but not dramatically. We just need to replace the constant perverse sheaf by the intersection complex, which coincides with the constant perverse sheaf if X is smooth, and otherwise it's something more interesting. Okay, and again, the reminder of what we do with this theorem, with the decomposition theorem, and really this has to do only with the splitting. So because the direct image is split on the previous slide, the natural morphism from the ith perverse truncation of the direct image to the direct image admits left inverse alpha. So that after taking global sections, this guy on the left, which we define to be the ith piece of the perverse filtration of the cohomology of X with respect to P, this has a morphism just given by applying the derived global sections functor to the morphism from the truncation to the full direct image. And this target you can more or less identify with the cohomology of X. This is injective because it's obtained by applying a functor to a morphism that has a left inverse. So it has a left inverse, so it must be injective. And yeah, the left-hand side is called the ith piece of the perverse filtration with respect to P. And the definition is functorial. I've already mentioned this. So if I have a morphism between split sheaves, I get a morphism of filtered complexes. And this perverse filtration will be the P in the P equals W conjecture. And the W is something we've also already seen, which is the weight filtration. But this is to come later. And again, just a reminder, so for any complex variety X, there's this category of thinking of these things as essentially enhanced perverse sheaves, mixed Hodge modules. There's a forgetful morphism or a faithful functor, which just forgets the enhancement and spits out the original perverse sheaf. And the only thing we're really going to keep track of is the weight filtration that is part of that enhanced structure. And a reminder of the standard conventions, a mixed Hodge module is called pure if the only jump in its weight filtration, pure of weight I, if the only jump in its weight filtration comes in position I. so that the associated gradient with respect to the wave filtration is concentrated in degree I. And an object in the derived category is called pure if all of the cohomology sheaves are pure of weight matching the cohomological degree. Purity, I've said this a couple of times, but I just want to emphasize it. Purity of a complex, it means that these perverse sheaves given by taking associated graded bits of the cohomology sheaves of F vanish for I not equal to J. And this is a local statement. The statement that a given perverse sheaf is 0 is something that can be checked locally. And this is crucial. And this is in contrast with the property of being split. If I have some complex in the derived category and I can show it's split on a cover, that's not enough to demonstrate that it is indeed split. And this is why throughout these talks, I've insisted on going the extra mile and not just showing that things are split, but actually pure in the land of mixed Hodge modules, because I want to be able to work locally for reasons that will become clearer. Okay, so the theorem, which I've slightly rearranged from the last time I presented it, comes in 2 pieces. So if F is a pure complex, then it is split. And what's more, the category of pure weight n mixed Hodge modules on X is semi-simple. So if F is a split complex, this tells us it's isomorphic to its total cohomology, and each of those cohomology mixed Hodge modules is itself semi-simple. And the Saito version of the decomposition theorem then amounts to the following, that if P is a projective morphism of varieties, then the derived direct image along P preserves pure complexes. So in particular, if you take the constant perverse sheaf on a smooth variety, this has an enhancement to a pure mixed Hodge module. So when I push it forward, it will split, and I split into its cohomology sheaves, and each one of those will be semi-simple. Okay, so so far, so much reminder of stuff I've already said. Now for finally a little bit of nonabelian Hodge theory. So this relates 2 sides. There's a nonabelian Hodge correspondence. And on one side, well, actually 3 sides, but in this talk there'll only be 2 sides. This is what's called the Dolbeault side, and it concerns Higgs bundles. So throughout this talk, C will denote a smooth projective complex curve of genus G, and a Higgs bundle on C is a pair F tilde, where F is a coherent sheaf on C, which will be locally free, and eta is almost an endomorphism of F, but it's slightly twisted. So it's a morphism from F to F, tense of the canonical line bundle on C. And this is commonly called the Higgs field. And we call the rank and the degree of this gadget, whatever the rank and the degree of the underlying coherent sheaf are. These objects form a category. So we define morphisms between these pairs to be morphisms between the underlying coherent sheaves, which commute with the Higgs field in the obvious sense, which I've spelled out here. And H tilde is injective if H is. Okay. And right, we're going to want to restrict to semi-stable Higgs bundles. So in order to get there, we'll have to define the slope. The slope of a Higgs bundle is defined more or less the same way as the slope of an ordinary vector bundle on a curve, say. In fact, yeah, it is the ordinary slope of the underlying vector bundle on the curve. It's the degree of F, moduli the rank, divided by the rank of F. And F tilde is semi-stable if for all sub-Higgs bundles, i.e. for all Higgs bundles admitting an injection into my given Higgs bundle, the slope is less than or equal to the Higgs bundle under consideration. And stable if these inequalities are all strict. So as a sort of general statement, or a way of tying into general statements that come later, the category so defined of Higgs bundles on C is 2 Calabi-Yau in well, various senses, one of which I've written here, that there are bifunctorial isomorphisms between X going one way between Higgs bundles and shifted X dualized going the other way. So this looks very much like Serre duality on a K3 surface, say, where the canonical bundle is trivial. And so usual Serre duality, where you'd usually see tensoring with the canonical bundle, becomes this simpler looking statement. And one way to see this, that there is this pairing, is indeed to use Serre duality. So a sort of favorite way of considering Higgs bundles is as coherent sheaves on the total space of the canonical bundle of my curve. This is a non-compact two-dimensional smooth variety with trivial canonical bundle. And so I can apply Serre duality for compactly supported sheaves to get this pairing. But however you arrive there.
So the X is taking the category of Higgs bundles, not just coherent sheaves. Okay, thank you.
Yeah. These are X in the category of Higgs bundles, okay, so these are Higgs bundles, which will be the players on one side of the nonabelian Hodge correspondence. And like I say, that side is called the Dolbeault side, and there are associated Dolbeault moduli spaces, which are just moduli spaces of Higgs bundles. So again, you fix a curve C, which, as throughout the talk, will be assumed to be smooth projective of genus G. Then we define the sort of, as throughout all of these talks, wherever you see a math frac M, that's a stack. Wherever you see a math cal M, that's a scheme. So math frac M dol RD is the moduli stack of semi-stable rank R degree D Higgs bundles on C. So there are numerous ways of constructing this. One way is to use the fact that Higgs bundles can be considered as coherent sheaves on the total space of the canonical, and use standard constructions of moduli stacks of semi-stable coherent sheaves. But if you like, you can just think of it as a virus function of points. But however you get there, there is this stack whose points are Higgs bundles of semi-stable Higgs bundles of rank R degree D. And this maps down to a coarse moduli space, which is this math cal guy. And the points of this coarse moduli space correspond to polystable Higgs bundles. So the morphism from the stack to the coarse moduli space should have a sort of familiar looking flavor, which is that if I have a semi-stable Higgs bundle, what that means is there might be sub-Higgs bundles of the same slope. But what I can do is take the Jordan-Holder filtration of this object in the category of semi-stable Higgs bundles of fixed slope, and then look at the subquotients of the Jordan-Holder filtration, and then take the direct sum of the subquotients. And that is the morphism that takes me from the stack to the scheme, because whatever that process spits out, it will be a polystable Higgs bundle, namely a direct sum of stable Higgs bundles. And this is very much like the Jordan-Holder map that we've been playing with in the first two talks. Yeah, okay, so just to repeat what I've just said. So what people historically or in the past have liked to do is to consider the case where R and D are coprime, because then this moduli scheme becomes smooth. This condition forces semi-stability to imply stability, which is a sort of familiarly nice property that buys you a lot of other stuff, like that this coarse moduli space is a fine moduli space. And what's more, under these conditions, the moduli stack is a C star gerb over the coarse moduli space, which just means that the fibers of P look like the classifying space of C star. So what this will mean is that the cohomology of the coarse moduli space is very closely related to the cohomology of the stack. It's basically the same thing as it tensor with the cohomology of BC star. Yeah, and people like this because then the coarse moduli space is smooth, and that makes life easier. In this talk, I'm going to veer away from this. I'm going to veer to the opposite extreme and try as hard as I can to understand the case where D equals 0, which is where things become as stacky and as singular as they possibly can be. All right, so Hitchin defined this map, which takes me from a Higgs bundle to well, the generalized eigenvalues of the Higgs field. So my favorite way of thinking of Higgs bundles is as coherent sheaves on the total space of the canonical bundle. This is the morphism that just remembers the support of those sheaves, but more explicitly, I've written it here. It just remembers the, well, yeah, I've written it here. It remembers these quantities. So in other words, it's picking out the eigenvalues of the Higgs field. Importantly, this morphism is projective, and so all of our favorite fun and games with the decomposition theorem comes into play. So in particular, for R and D coprime, since this coarse moduli space is smooth, the constant perverse sheaf on it is pure, and I can apply the decomposition theorem to it. In particular, the direct image along H, along the Hitchin map, will split. So via the usual technology that we've seen a few times now, the cohomology of this coarse moduli space acquires a perverse filtration with respect to H, which is defined explicitly as follows. Yeah, so what have I done here? Yeah, so again, using the fact that H is projective for all R and D, i.e. even if R and D aren't coprime and we don't have the coarse moduli space is smooth, as reminded on the first slide with any content on it, the intersection complex gives us a sort of way of still applying the decomposition theorem. So even under these circumstances, I can take the direct image of the intersection complex, and that splits, and so the intersection cohomology of the coarse moduli space in any case will have a perverse filtration.
What is the support of the direct image?
Not known. Not known. There is a recent-ish, maybe not that recent because it's pre-pandemic, but within the last few years, paper by Heinloth, De Cataldo and Migliorini, I think, which really investigates this. I don't know. It's the short answer. Yeah, I don't know. Okay. Right, so that wraps up the Dolbeault side. The other side is the Betti side, and that's going to be defined as follows. So this has a much more topological flavor. So what we do is we take our curve and we basically forget everything about it apart from the genus. So we remember the underlying topological space, and we're just going to consider the fundamental group algebra of that underlying topological space, which only depends on G. So let sigma G be a genus G compact Riemann surface. Sigma G prime be the same object, but with a puncture. Why have I changed C to X? Okay. Yeah, some puncture for some C inside here. I wonder why I've done that. Oh, I think I use X later. Okay, so sigma prime G is the punctured Riemann surface. Then we have the standard presentations. The fundamental group of the genus G Riemann surface is given by the free group on 2G generators, modulo one relation. The product of the commutators is to be the identity. And for the punctured Riemann surface, I just remove that. I remove that relation. Okay, so I'm going to following my usual convention that math frac M is a moduli stack, math cal M is a moduli space, I let math frac M Betti GRD be the stack of R-dimensional representations for the fundamental group of the punctured Riemann surface, where the action of the product of the commutators is multiplication by this rth root of unity. So if I'm thinking of representations of the fundamental group as local systems on my Riemann surface, what this is saying is that the monodromy around the puncture is given by multiplication by a scalar, and that scalar is this rth root of unity. Yeah, this is also not what I want to say. So if D is a multiple of R, this is what I want to say here. Yeah, then this exponential just becomes 1. And so this M Betti GRD becomes the same as the representations of the fundamental group of the full Riemann surface. So R-dimensional representations of the fundamental group of, yeah, pi1 of, sorry, R-dimensional representations of pi1 of sigma G. Yeah, and mathcal M Betti is the coarse moduli space. So as always, points given by sort of semi-simplification. So in this instance, points correspond to semi-simple modules for the fundamental group of the punctured Riemann surface, such that the product of the commutators is given by multiplication of by this rth root of unity. And like on the Dolbeault side, as long as R and D are coprime, then this moduli space is smooth, and the stack is a C star gerb over it. Yeah, this isn't a coincidence that on both sides you have the smoothness at coprime R and D, because the two sides are related by nonabelian Hodge theory. So as always, we fix here smooth projective genus G curve, and for all R and D, there is a homeomorphism, and this is important. It's not a isomorphism of algebraic varieties. It's just a homeomorphism of the underlying topological spaces between the coarse moduli space on the Betti side and the coarse moduli space on the Dolbeault side. So passing to cohomology, there's an isomorphism between the singular cohomologies of these two objects. But one thing to point out right at the outset is that the left-hand side and the right-hand side both have mixed Hodge structures, because we're taking the singular cohomology of algebraic varieties. And this morphism here does not respect the mixed Hodge structures. Indeed, one can show that at least if R and D are coprime, the target, the mixed Hodge structure, is pure, whereas for the domain, the mixed Hodge structure is impure and is somehow the main object of study in the P equals W conjecture. Okay, so the theorem is very much at the level of the coarse moduli spaces, but at least if R and D are coprime, we can sort of, in a very cheap way, upgrade it to a theorem about the stacks. Because as I've mentioned, the cohomology of the stack is just the cohomology of the coarse moduli space tensored with the cohomology of the classifying space of C star. And that comment applies on both sides, the Betti and the Dolbeault side. So given the isomorphism between the cohomology of the coarse moduli space on the Betti side and on the Dolbeault side, we get a sort of very cheap isomorphism between the cohomology of the stacks. Yeah, I want to say that for R and D not coprime, coming up with such an isomorphism is going to be a lot of hard work. For all R and D, because intersection cohomology is a topological invariance, we get an isomorphism between the intersection cohomology of the Betti moduli space and the intersection cohomology of the Dolbeault moduli space. That also will be important later. And yeah, here's the conjecture. This version due to Cataldo, Hauser, Meglierini. If R and D are coprime, so everything is smooth, then this isomorphism between the cohomology of on the Betti side and the cohomology on the Dolbeault side takes the weight filtration to half the perverse filtration with respect to the Hitchin map. I've put the indexes for these filtrations in red because this is strange and important that there's a halving in the degrees. And as a sort of side comment, it probably should be called the P equals H conjecture because it's known that the Hodge filtration on the left-hand side is exactly half the weight filtration. But
So
yeah.
may I ask, I mean, it's just a homeomorphism. There are many of them. Why either kind of, if it preserves some filtration, then what? Any homeomorphism preserves?
Oh, okay. No. Okay, so they construct an explicit homeomorphism between. So this, so like I say, there's this halving of the degrees going from the weight filtration on the Betti side to the perverse filtration on the Dolbeault side. And the sort of obvious generalization of this to the non-coprime case, and this conjecture I think is due to Decomposition and Maulik, is that the induced isomorphism between the intersection cohomology on the Betti side and the intersection cohomology on the Dolbeault side, again, just halves the degrees. And this is strictly a generalization of the P equals W conjecture, because if R and D are coprime, the intersection cohomology is just the usual cohomology. Okay. So so the point of the talk is going to be to try to extend the P equals W conjecture, or come up with and try to prove a stacky P equals W conjecture. So a P equals W conjecture at the level of the moduli stacks, not the moduli coarse moduli spaces. Okay, so it's going to be hard, but let me sort of in this slide do a sort of first pass. So we need a perverse filtration on the Dolbeault side. So let's go ahead and just try to define it in the most obvious way. We define the stacky Hitchin map from the stack of Higgs bundles down to the usual Hitchin base in the same way as Hitchin did. We just take the generalized eigenvalues of the Higgs field. Let me point out, because it will come up later, that this stacky Hitchin map, I can decompose it as the morphism from the stack to the coarse moduli space, followed by the usual Hitchin map. Again, in terms of my favorite way of thinking of Higgs bundles, the morphism from the stack to the coarse moduli space takes me from semi-stable coherent sheaves on the total space of the canonical to the underlying polystable, which has the same support as it. So that's why you have this factorization. But anyway, it's defined in the most naive way possible. We just take a Higgs bundle and we send it to the generalized eigenvalues of the Higgs field. Okay, so here's the conjecture. I put it in inverted commas for reasons that will become clear by the end of this slide. So firstly, the first part of the conjecture is that there exists some isomorphism. And remember from last time, when we're confronted with a singular stack or singular variety, my favorite invariant of it is the Borel-Moore homology. So that's something that coincides with the cohomology in the smooth case, but in the non-smooth case is a cohomology theory, which is somehow more responsive to the singularities. So with that in mind, the sort of obvious way to generalize the conjecture is to say that there is an isomorphism between the Borel-Moore homology on the Betti side, on the Betti stack, and the Borel-Moore homology of the Dolbeault stack. Okay, so that's the first part. The first part says that there is a nonabelian Hodge correspondence at the stacky level. And then the second part says that whatever this is, and I should say, it may be preempting a repeat of Jan's question from a couple of slides ago, this should be a natural isomorphism. There should be a sort of canonical construction here. It shouldn't just be any old isomorphism. And the second part of the conjecture says that for this natural isomorphism, the weight filtration gets sent to the perverse filtration with respect to this stacky Hitchin map, but again with this halving of degree. And yeah, so right, okay, so that's the sort of first pass at a stacky P equals W conjecture. But there are at least 3 serious problems. Firstly, in order to work with perverse filtrations, in order for them to be nice, we've always assumed that the thing where the thing splits. Remember, I keep saying this over and over again. The point is that if this complex, say this derived direct image of the dualizing complex, splits, then the morphism from the truncation of it into it has a left inverse, so that the perverse filtration, as I've defined it, gives me a nice filtration. So far, we've received no assurance that actually this thing does split, because, well, this complex isn't pure. This morphism, it will turn out, is approximated by proper maps, but yeah, I mean, because this complex isn't pure, that isn't enough to get us purity quickly. Okay, so that's the first problem. Second problem is, and this probably is the most daunting, is that we haven't constructed this isomorphism between the Borel-Moore homology of these 2 stacks. I mean, there is no nonabelian Hodge theoretic correspondence between these 2 stacks, and somehow we have to find a way to repeat the work of Simpson et al. In order to get around this. The third problem, and this is probably the most worrying, is that the conjecture is in fact false. So in one of the few instances that we can actually make sense of, or just deal with 1 and 2 quickly, we soon realize that actually the conjecture is false. So yeah, so far it's not looking super promising, but the point of the rest of the talk is to address these 3 problems via the decomposition theorem for 2 CY categories. So before I get onto that, let me explain this point 3, because apart from anything else, it's quite quick. So set G equals 0. So let's say we're looking at a genus 0 curve, i.e. P1, and take a semistable rank R degree 0 Higgs bundle on it. By Grothendieck's theorem, the underlying coherent sheaf is a direct sum of line bundles. So these are Serre twists of the structure sheaf on P1. But in fact, semistability forces all of the AIs to be 0 apart from A0, which is equal to R. Essentially because if you take the summand of this F consisting of all Serre twists above a certain I, that will be stable under the Higgs field. So it will destabilize the bundle unless it's either 0 or the whole thing. So yeah, there can't be more than 1 type of Serre twist appearing in this direct sum decomposition. And so then, because there are no sections of the canonical bundle on P1, the Higgs field itself will be 0. So in fact, there is only 1, up to isomorphism, only 1 Higgs bundle, only 1 semistable degree Higgs bundle of rank R. So we get this commutative diagram. The stack of the Dolbeault stack just looks like the classifying stack of the stabilizer of this Higgs bundle, which is GLR. The Hitchin base, which is recording all of the possible eigenvalues for all of the Higgs fields, is just a point because there is only 1 Higgs field. And so, yeah, the morphism from the Dolbeault stack to the Hitchin base just looks like the morphism from BGL R to a point. So H is really the structure morphism in disguise, which means that the perverse filtration defined with respect to it just winds up being the filtration by cohomological degree. Because, yeah, the perverse T structure on the derived category of coherent sheaves on a point is just the usual T structure. On the Betti side, things are pretty similar. The fundamental group of P1 is just trivial, so a representation of it is just a vector space. So in particular, there's only 1 rank R representation, its stabilizer again looks like GLR. So the Betti stack looks like point mod GLR. The mixed Hodge structure on this stack is pure. This is this is in Delene mixed Hodge 3, I think. So one of the first things ever proved about mixed Hodge structures. So in particular, by definition, that means that the weight filtration is the same as the filtration by cohomological degree. Okay, so it's not hard to come up with an isomorphism of stacks between the Betti side and the Dolbeault side. So in particular, it's easy to come up with an isomorphism of cohomology. But there's no halving of the weight degrees. They just agree. The weight degree is the same as the cohomological degree on the left-hand side, and the perverse degree is the same as the cohomological degree on the right-hand side. And I should say, in case it's causing confusion, that I've violated my plan of using Borel-Moore homology throughout here, because all of these stacks are smooth. So this is an instance where Borel-Moore homology just recovers usual singular cohomology. So this is a big problem. The P equals W conjecture says that the degrees are halved when I go from the weights to the perverse filtration, but here we see that this just doesn't happen. And as a sort of desperate last move, you might imagine, well, maybe the correct formulation of the P equals W conjecture for stacks doesn't have this halving of degrees.
Maybe the genus should be bigger than 0, because there are some very special properties of the stack for G equals 0.
Right. But in genus 1, you see that both versions of the P equals W conjecture fail, the one where you halve the degrees and the one where you don't. That takes a lot of work, but it's true. So there's no quick fix for this. And so we're going to have to do a little bit more work just to come up with a reasonable formulation of the P equals W conjecture for stacks. Okay. So that is going to come via this theorem, the decomposition theorem for 2CY categories. So let me just give you some examples of 2CY categories, and they will include the examples we've seen in the last 3 talks, or the last 2 talks. So firstly, Higgs bundles on a smooth projective curve. Secondly, the Betti side, representations of the fundamental group of a compact genus G Riemann surface. Categories of modules over pre-projective algebras in all their various flavors. So in the last talk, I just talked about ordinary pre-projective algebras, but there are variants of these, and they all wind up spitting out 2CY categories. Fourthly, compactly supported coherent sheaves on a smooth projective surface. Oh, I don't need the word projective here. Compactly supported coherent sheaves on a smooth surface S satisfying omega S is trivial. So as I've sort of alluded to, if I go ahead and delete the word projective here, example 1 is a special case of example 4. And then example 5, which is kind of exotic, and I'm not really going to say very much about it except to exclude it from various theorems, because nets off components. So if there's anyone in the audience who likes those, then
it's something which is left after a semi-orthogonal decomposition of something.
Right. So it's a sort of a weird looking component in a semi-orthogonal decomposition, which shares the categorical properties of the derived category of coherent sheaves on a K3 surface.
Yeah, but since you mentioned multiplicative pre-projective algebras, why you didn't mention the stack of connections on the curve, which is
because I didn't want to muddy the waters with a third part of the nonabelian Hodge correspondence. But yes, of course, that's another example of a 2CY category.
They will be all okay for whatever theorem you will formulate later.
Yeah. Except for 5, which I'll have to be a little bit careful with. But I'll come on to that. So
yeah, but will kind of before you formulated it, will it be like if you take one of these 5, 6, or 10 examples, then something is true, or
Yes.
there will be a class of two Calabi-Yau categories, which is formulated in kind of more general terms.
Yes, to that.
Inconstructible, locally Artin or something, yeah, with this.
Yeah, I mean, I haven't written any of the words in these slides because I didn't want to alienate everyone. But yeah, so what I'll be interested in is what are called left two Calabi-Yau categories. So these are categories with some kind of cyclic structure. And furthermore, I'm going to place certain demands on the moduli stack of objects in these categories.
What kind of, or it will take you too far from
no, I mean,
yeah, I mean,
the audience is
what kind of, because, you know, if you take just a category, you cannot do algebraic geometry on the stack of objects because there is no stack of objects.
Right, so I'm looking at finite type left 2CY DG categories for which I can take the derived stack of objects.
Okay.
But of course, I don't want to take the derived stack of objects, so I insist that the classical
you
truncation,
truncate, yeah.
Yeah, the classical truncation of some open substack of the derived stack of objects in my category has a good moduli space in the sense of alpha. Okay, so it's a very general setup, but I didn't want to.
Okay. Just checking. Okay, good.
Yeah. So again, this is a general condition which I'm not expecting everyone to be familiar with. So I restrict to moduli stacks which have a good moduli space. So in what this means concretely in cases that we're going to care about is that in cases 1, 4, and 5, I can't take the stack of all objects. That won't have what's called a good moduli stack. Rather, I have to restrict to semi-stable objects. And so this P always will be a kind of semi-simplification morphism. So for modules, it really is a semi-simplification morphism. For coherent sheaves or semi-stable coherent sheaves, it sends me to the associated polystable. But I have to, for coherent sheaves, I have to impose stability conditions in order for this to work out. But that's fine. That's going to be fine for nonabelian Hodge theory because we explicitly restricts on the Higgs side to semi-stables. And here's the sort of small technical point that in all cases, apart from the fifth, the moduli stack of objects in a Kuznetsov component, they have known global quotient presentations. So these are all, once I restrict to semi-stables for coherent sheaves, this is a global quotient stack.
What is it for Higgs bundles? What is this global? So which means that it's just quotient of variety.
Yeah, I'm not sure who to attribute this to. I mean, again, you can, like if you think of Higgs sheaves or Higgs bundles as coherent sheaves on the total space of the canonical, you can compactify the canonical bundle however you like, and then take semi-stable coherent sheaves on that projected variety, and restrict to the open locus where the support avoids the line at infinity. Yeah, and that'll get you into the land of coherent sheaves on a smooth projective variety. And there's the I mean, the usual construction of the coarse moduli space is as a GIT quotient, and you just take the stack equations of the same space by the same group to get the stack of semi-stable coherent sheaves. I can't tell if you're happy with my explanation.
Maybe not.
Maybe not.
Go
Okay.
ahead. Yeah.
Yeah, okay. So yeah, the main theorem is that if I take one of these stacks, and I assume that this has a good moduli space, so I restrict for coherent sheaves, I restrict to the semi-stable coherent sheaves. Then if I take the ith cohomology mixed Hodge module of the push forward of the dualizing complex, it is pure of weight I. And what's more, it vanishes for I, not a weakly positive even number. As long as I'm not in the Kuznetsov component case, then this derived direct image of the dualizing complex is itself well-defined and pure. So pure just means that the cohomology sheaves are pure of weight I. And the sort of annoying wrinkle here is that unless the moduli stack is a global quotient stack, I don't know how to define the derived direct image of the dualizing mixed Hodge module. But for non-abelian Hodge theory, this just won't come up for us. And we will use the fact that this derived direct image of the dualizing complex makes sense in the derived category and is pure. Okay, yeah, so in particular, this complex splits. And so we get a perverse filtration on the Borel-Moore homology of the stack. Okay, so that's one corollary, but we wanted something else. We wanted that the derived direct image along the Stacky-Hitchin map splits. But remember the Stacky-Hitchin map factorizes as the morphism to the coarse moduli space followed by the usual Hitchin map. The theorem says that the derived direct image along the morphism to the coarse moduli space is pure. And then because H is projective by Saito's original version of the decomposition theorem, it preserves pure objects. So this push forward to the Hitchin base from the stack is itself pure. And so we get the perverse filtration on the Borel-Moore homology of, oh yeah, there should be a BM here, sorry, of the Borel-Moore homology of the Dolbeault stack. So that's problem 1 solved. Okay, so
what was problem 1? Sorry.
Problem 1 was in order to define the perverse filtration, we assumed that the derived direct image of the dualizing complex was split.
Yeah, okay.
Okay, so I'm not going to give all of the details of the proof of the decomposition theorem for TCY categories, but the two main ingredients are an étale neighborhood theorem and the theorem that we've already seen for pre-projective algebra. So if you'll excuse me skipping back one slide. In the case where C is the category of representations of a pre-projective algebra, we've actually already seen this theorem. This was in the last talk. One of the main results was that the derived direct image of the dualizing complex was pure. We even wrote down explicitly what it was in terms of BPS sheaves and sim of them with cohomology of BC star. And so everything lived in even positive perverse degrees. So we've already seen this theorem for pre-projective algebras. And the second ingredient of the theorem is going to be a reduction to that case. So the first part of that reduction is a formality statement, which goes as follows. I take some collection of simple objects in one of my 2CY categories. Then the A infinity Yoneda algebra of this collection of objects is formal, which means, well, what does it mean? It means that at the level of, how do I want to explain this? At the level of the DG categories that these things live in, the Arholm algebra, or the Arholm endomorphism algebra, the direct sum of these objects is isomorphic to its, or quasi-isomorphic to its cohomology. Or I can express it the way I've done here. The key here is that the A infinity Yoneda algebra of this collection of objects controls all of the deformation theory of any extensions of these objects. I should say, since I'm in this seminar, this is the point of view on deformation theory that I learned from Konsewicz and Jan Soderman's notes on A-infinity deformation theory. So up to an isomorphism of A-infinity algebras, this fancy infinity and Ada algebra is just a graded associative algebra. So that algebra determines all of the deformation theory of extensions of these objects via just deformation theory. But by the 2CY property, it turns out that that algebra itself is defined by a very small amount of data, namely the dimensions of the x's or the x1s going between these objects. There are no HOMs going between them because we're assuming that they're distinct simples. There are no x2s going between them because by the Calabi-Yau2 property, x2s are duals to x0s or HOMs. And it turns out that this whole algebra is determined just by these dimensions, just by some combinatorial data. What that will buy us is that it tells us exactly what a formal neighborhood of the extensions of these objects looks like in the stack of all objects. But next, and this next theorem, it really relies on a lot of recent and less recent work by Alper, and especially a paper of Alper, Hall, and Reed, which you should read as kind of art in approximation, but really beefed up for the 21st century. So yeah, it will turn out that knowing this fact about formal neighborhoods tells us that formally locally, our stack of objects looks like the stack of representations of a pre-projective algebra. And what their theory enables one to do is beef that up to a statement about étale neighborhoods. So explicitly, I take some collection of simple objects in one of my 2CY categories. I take the point in the moduli stack representing some direct sum of these objects. These exponents di's you can think of as being like a dimension vector. So then I define a quiver which has as vertices these distinct simple objects, and I give this quiver enough arrows so that when I double it, I get the xth quiver of the FIs. So once I double Q, the number of arrows going from Fi to Fj is the number of x1s, or the dimension of the x1 space from Fi to Fj. Then we get the following. There's this commutative diagram where on the left-hand side, I have the Jordan-Holder map from the stack of representations of the pre-projective algebra to the coarse moduli space. And on the right-hand side, I have the morphism from my moduli stack of objects in C to the coarse moduli space. And what this is saying is that around the origin on the left-hand side and X on the right-hand side, there is a common étale neighborhood on the base, such that moreover, the stacky pre-images of those two neighborhoods are also isomorphic. So étale locally, the whole theory of this morphism, this P morphism, is governed by the JH morphism for pre-projective stacks.
Is there a three-dimensional analog of this?
You mean like for an arbitrary 3CY
for three Calabi-Yau from a reasonable class? Étale neighborhood is just quiver with a potential in the similar way.
So the closest I can think of is the result of Toda saying that if I take coherent sheaves on a projected 3CY variety, there's a result like this, but where étale neighborhoods can be replaced by analytic neighborhoods.
Mm-hmm.
Since I've mentioned that result, I should probably mention why I'm not using it. I mean, one could take his result, at least for coherent sheaves on K3 surface, and get a result like this, but with analytic neighborhoods everywhere. The reason for pushing for an étale version of everything is, again, a technical thing regarding mixed Hodge modules, namely the category of analytic mixed Hodge modules is a disaster to work with. And in particular, derived functors, derived categories of analytic mixed Hodge modules are, yeah, I mean, the six-functor formalism is somehow not there. So
With 3 Calabi-Yau case, there is no Ital version. Yeah? Or it's not true. What's the status?
Okay. If I can come up with a if the A infinity Yoneda algebra is quasi-isomorphic in the cyclic sense to one where for sufficiently high n, the nth higher products all vanish, i.e. the potential looks kind of polynomial and not formal.
Yeah.
Then,
I see.
Then you're fine.
I see. So it's a question about algebraicity.
Yeah, the formality here is strong, and in particular buys this algebraicity. It's saying that there are no higher, I mean, up to quasi-isomorphism, there are no higher products. So you don't have to worry about.
And the pre-projective relations, how do you see them? Why not just a double quiver or something? I mean, like.
Well, because if you take, so if you look in the first box, buried here is the statement that if I have a cyclic 2CY category where the only endomorphisms are of between objects are just scalar multiples of the identity, then this category has a very particular form. This in particular is this is a result of G-Ren, in fact, in these terms, right?
I asked here, it's just a version of
right. This, I mean,
paper.
This is precisely that result.
Okay.
If you take the cyclic, sorry, if you take if you take that A infinity algebra and just take its causal dual, you get the pre-projective algebra, and that's how you get to pre-projective algebra.
Now I see it. Okay, thank you.
Yeah. Okay, so to remind everyone of what we're trying to do, we're trying to show that for this morphism from the moduli stack to the moduli space, the ith cohomology mixed Hodge modules are pure of weight I, and that they vanish if I isn't a positive even number. But as I said a long time ago now, purity is a local property in any one of the following three topologies, i.e. it's the statement that certain perverse sheaves vanish. And similarly, the vanishing property is obviously a local property. So this vanishing for I not equal to positive even number. Okay, so you can probably see what's going to happen next. We pick some x in the coarse moduli space representing this polystable object f, and then we bring the Ital neighborhood theorem from the previous slide forward. We have this diagram where all of the horizontal maps are Ital. And so it follows that purity of this, purity of weight I of this ith cohomology sheaf is equivalent to the purity of weight I of the ith cohomology sheaf of the push forward along JH. But that's exactly what we proved using the cohomological DT theory of pre-projective algebras. So that was sort of the main result from the second talk. And likewise, from the second talk, we proved the required vanishing of odd or negative cohomology at the level of pre-projective stacks. So that finishes the proof, or finishes the sketch of the proof of the 2CY decomposition theorem. And that solves the first problem. That tells us that the perverse filtration with respect to the stacky Hitchin map at least makes sense. Okay, so back to this stacky P equals W conjecture. I can now fix it. I mean, remember the third problem was that the conjecture was just straightforwardly false. Using the perverse filtration with respect to the map P to the coarse moduli space, we can fix the stacky P equals W conjecture, and we can fix it in two equivalent ways. So yeah, there are filtrations on the Borel-Moore homology of the Betti stack and the Borel-Moore homology of the Dolbeault stack with respect to P, because of the main theorem that the derived direct image of the dualizing complex along P splits. And we use that filtration to fix the stacky P equals W conjecture. So the first version looks a little bit neater, and it's the following claim. There exists a natural isomorphism from the zeroth piece of the perverse filtration with respect to P of the Betti Borel-Moore homology of the Betti stack and the Borel-Moore homology of the Dolbeault stack. And what's more, this natural isomorphism sends the 2ith piece of the weight filtration on the left-hand side to the ith piece of the perverse filtration with respect to the stacky Hitchin map on the right-hand side. So the right-hand side you can think of as the intersection of the ith piece of the perverse filtration with respect to the stacky Hitchin map, the intersection of that with the 0th piece of the perverse filtration with respect to the map P to the coarse moduli space. So that's cleaner than the second version, but kind of unsatisfactory because we're only addressing part of the Borel-Moore homology. We've restricted all of our attention to the 0th piece of the perverse filtration, which might feel a bit limited. So there's a second version, which is the claim that there is a natural isomorphism between the Borel-Moore homologies of these two stacks. And what's more, the 2ith piece of the weight filtration on the left-hand side gets sent to this. And this is where things, this is not so clean, but I mean, it is a statement that concerns the whole Borel-Moore homology. So again, there's a kind of fixing of the, or modifying of the perverse filtration with respect to the stacky Hitchin map by something involving the perverse filtration with respect to the P map. And okay, so for the rest of my time, I'm going to try to motivate these conjectures. So firstly, as a sort of sanity check, they're both true for genus less than or equal to 1. So for example, let's look at the second conjecture in genus 0. Well, what you get there is that the perverse filtration with respect to the stacky Hitchin map agrees with the perverse filtration with respect to P because they are the same map. And so you get that the conjecture claims that the weight filtration gets sent to the perverse filtration. So that's what we found. In genus 1, things are an awful lot less trivial, but again, these conjectures can be verified. Yeah. Okay, so I want to motivate these conjectures by pointing out that they slot in with existing conjectures. So this slide is about the stacky P equals W conjecture implying the P equals W conjecture for intersection cohomology. And this relates to sort of picking apart the decomposition as we started to do at the end of the second talk. So just a reminder that for P, the morphisms of the coarse moduli space, we've shown that the derived direct image along P of the dualizing complex splits, and each mixed Hodge module is semi-simple. So as in the case of the moduli stack of representations of the pre-projective algebra, once we, the first thing to try and do is to try and work out how do these semi-simple perverse sheaves split up, what are their supports, so on, the usual games. And the first move in the game is very easy. The first move is to observe that the 0th perverse cohomology or the 0th cohomology of the mixed Hodge module complex has a summand which is just the intersection complex on the coarse moduli space. And then there's some complement which is supported on deeper strata. So passing to hypercohomology, that gives me an inclusion of the intersection cohomology of the coarse moduli space inside the, and again, this should be the Borel-Moore homology of the Dolbeault moduli stack. So there's an intersection of the intersection cohomology inside the 0th piece of the perverse filtration of the Borel-Moore homology with respect to P. And what's more, because this comes from a inclusion of sheaves or complexes on the coarse moduli space, it respects, by the sort of functoriality that I reiterated of taking perverse filtrations, this inclusion respects the perverse filtrations with respect to the Hitchin map. Similarly, there's an inclusion of the intersection cohomology inside the, this time I've remembered it, the Borel-Moore homology, or the 0th piece of the Borel-Moore homology with respect to the perverse filtration on the Betti side, and this respects mixed Hodge structures because it comes from an inclusion of mixed Hodge modules. So as long as whatever our natural non-abelian Hodge theory isomorphism is, it respects these inclusions, and we'll see on the next slide that the candidate does respect these inclusions, then the stack P equals W conjecture will imply the P equals W conjecture at the level of intersection cohomology, because it will be saying that this, that the intersection cohomology on the Dolbeault side is sent to the intersection cohomology on the Betti side. Since we're sitting in the 0th piece of the perverse filtration with respect to P, both versions of the stack P equals W conjecture tell us that there's this halving of degrees from the weights to the perverse degrees. So yeah, just using, again, purity, semi-simplicity, decomposition theorem, we get that the stack P equals W conjecture looks like it should imply the P equals W conjecture for intersection cohomology. Okay, so as a final slide, let me explain how conjecturally to deal with problem 1. Problem 1 was that there is no non-abelian Hodge theoretic isomorphism between the Borel-Moore homology of the Betti stack and the Borel-Moore homology of the Dolbeault stack, at least not yet. Okay, so we need to sort this out. The hardest case is D equals 0, because that's where things are the most stacky, most singular. So let me just focus on that case for the rest of this slide. And the idea there is something we've seen throughout all 3 of the talks. Namely, we want to prove something about some very large cohomology, whether it be the cohomology, the vanishing cycle cohomology of representations of a quiver, or Borel-Moore homology of representations of a pre-projective algebra. The way we do it is we show that that object is generated as an algebra by something much smaller, BPS Lie algebra, say, and then prove it at the level of the BPS Lie algebra. So this is how we address the purity problem in the previous talk, for example. Okay, so let's just start down that track. So mimicking the construction in the case of pre-projective algebras, the direct image of the dualizing complex on the Betti side, it carries a multiplication in this category, where this category has a tensor structure given by convolution as usual, given by pushing forward along the direct sum map. And yeah, that's an old result. We have a PBW isomorphism between this algebra object in this category of mixed Hodge modules in the coarse moduli space and the free supercommutative algebra generated by this guy on the right. So we've got some BPS mixed Hodge modules, tensor them with the cohomology of BC star, take the free supercommutative algebra, and there's a kind of PBW isomorphism between the two. What's more, we can go deeper. Instead of trying to prove something about BPS itself, at the end of the previous talk, we arrived at this conjecture saying that the BPS Lie algebra, at least for pre-projective stacks, is itself free as long as the quiver satisfies certain conditions, which are satisfied here. So as long as the genus is 2 or more, the conjecture becomes that the BPS Lie algebra, or this BPS sheaf, is a free Lie algebra generated by something precise, generated by the intersection complexes, and likewise on the Dolbeault side. Okay, so now we're almost there. We have this classical non-abelian Hodge theoretic isomorphism between the coarse moduli spaces, which gives a isomorphism between the push forward of the intersection complex from the Betti side and the intersection complex from the Dolbeault side. So in particular, if I take the free Lie algebra generated by one of those things, it will be isomorphic to the free Lie algebra generated by the other. So according to all of these conjectures put together, the BPS cohomology from the Betti side gets naturally sent to the BPS cohomology on the Dolbeault side via the classical nonabelian Hodge theoretic homeomorphism. Okay, so we sort of build the stack theoretic nonabelian Hodge theoretic isomorphism by bootstrapping it from an isomorphism between intersection complexes. So in particular, the condition that we had on the previous slide, that whatever nonabelian Hodge theoretic isomorphism we pick preserves the intersection cohomology as a subobject, is satisfied. What's more, we get that the implication goes two ways. So if the weight filtration on the intersection complex on the Betti side gets sent to half the perverse filtration on the Dolbeault side, then this remains true after sort of passing to the free Lie algebra objects generated by these two objects. So we get to sort of prove the P equals W conjecture for these very small objects, these intersection complexes, and then kind of transmit the conjecture through the free algebras or free Lie algebras generated by these objects. Yeah, okay, so that's all I wanted to say about that. So thanks very much for anyone who's made it this far, and I'll stop there and take questions.
Yeah, thank you very much. So do I understand from your very last line that you use classical nonabelian Hodge theory, and then, I mean, the map comes from classical nonabelian Hodge, and you just take this, whatever, classical psi, you use classical psi, so that's your point. But is it clear why, I mean, whatever explanation or approach to P equal W, is it clear why the weight filtration should be halved? Why 2I should correspond to I? I do not see any reason except of...
Yeah, just, I mean, you know, I've seen talks by the originators of this conjecture who, you know, who say that when they first presented it, people just sort of, you know, laughed. Like there's no heuristic. There's no, I mean, maybe I'm displaying my ignorance, but there's this, there's the obvious observation, which is that for rank 1, you're going from you know, C star to the 2G to to an elliptic curve to the Gth power, and there you see that there's this kind of halving going on, and then I don't know how you go from there to the P equals W conjecture, but this is what those three authors did, and it's proved in rank 2, right? So I mean, and there things are so complicated that it feels pretty hard to imagine that it could be true in rank 2 and then fail. I mean,
yeah, so
I'm being recorded, so
sort of no conceptual understanding, but rather difficult proofs. So that's why people should believe that it's true at all. But there are some special cases when it's true.
There are some special, very demanding cases where it's true.
Yeah.
And yeah, so if I had to sort of guess what in the future will be the heuristic reason that people give for the P equals W conjecture being true, assuming that it is true, will be something like this, that well, I'm hoping it'll be something like this, that it's true in low rank for silly reasons. And then that truth kind of transmits into higher rank because the Hall algebras under consideration are generated in low rank. Now, that the version of that statement that I've just given at some level must be false, because the point of the previous lecture was that there is cuspidal cohomology in higher ranks. So probably there will be some sort of fancy footwork between the Hall algebra for Higgs bundles with nilpotent Higgs fields and spherical generation there. I don't know.
Cohomological,
yeah.
cohomological Hall algebra for
yeah.
But kind of no induction on the genus, because in some other things people like to degenerate the curve itself.
Yeah, maybe that.
Okay, maybe let's other people ask questions, because I have few more and I don't want kind of to. So questions, please.
Let me ask a very naive question. So why call it non-abelian in this case? Non-abelian Hodge field.
Oh, because for R equals 1, you recover usual Hodge theory.
Oh, I see. So the rank 1 case, that's the standard abelian case. So for the higher rank.
Yeah.
Now, my second question is on also the last slide here. You are doing all these freely algebras over the intersection complexes. So in which category are you doing this freely algebra?
Right. So these intersection complexes, they live in the category of perverse sheaves on the coarse moduli space.
Okay.
And that coarse moduli space has this strange convolution tensor product where,
and also with a good braiding, actually, it's a symmetric.
Right. It respects the grading. I mean, the point is that the direct sum map that takes me from 2 copies of the coarse moduli space to 1 copy of the coarse moduli space is itself symmetric.
Okay.
So the tensor product on the category of perverse sheaves I get by convolving along that map is symmetric.
So in this case, there's the direct image of P of the perverse of this dual, which actually is a commutative algebra in that category. Am I right? When you take the symmetric of the PBW of the BPS direct sums of BPS.
It will be so if I just look at the just tell me if I'm misunderstanding the question. If I look at the 0th perverse piece here, I end up with the free associative algebra generated by the intersection cohomology, because it's the universal enveloping algebra of a free Lie algebra. So I just get all sort of tensor powers of BPS with itself.
So I try to I don't know whether that's corresponding to a symmetric algebra or corresponding to the universal enveloping algebra, which is not commutative.
Right. Yeah. It's yeah. I mean, this will be very far from being commutative.
Okay. I see. Okay.
In genus 1, you get something commutative, but I've restricted to genus greater than or equal to 2.
Okay, I see. Thank you.
More questions? Okay, then I have a few questions. So one is, it's sort of, since it's a seminar where some people like, mirror symmetry for categories, I remember, okay, good. Sort of, I speculated long ago about a version of P equal W, which involves these things. Namely, you mentioned several times that Higgs bundles is just coherent shifts on the cotangent bundle to the curve on the total space.
Yeah.
Okay, so now you can replace this particular symplectic surface by any other symplectic surface. Yeah, and there are plenty of them because you can throw away zeros of the canonical shift from any project.
Sure.
Yeah, okay. There are now then you can speak about analog of Higgs bundles in terms of coherent shifts, like maybe pure dimension 1 coherent shifts on the surface. And if you do not like that it's non-compact, then you can impose some conditions on the compactification or partial compactification. Anyway, you have this category which is on the Dolbeault side. Now, what's on the Betti side? And so I claim that on the Betti side, you will have the Fukaya category instead of representations of the fundamental group. You will have the Fukaya category of this surface. It's complex dimension 2, so it's real dimension 4. And you take in fact, it's partially wrapped Fukaya category for which the symplectic form is the real part of your holomorphic symplectic form, but imaginary part is not thrown away, it appears as a B field. So there is a Fukaya category. Now, if you apply this to the conventional story, then you can prove that indeed on the Betti side, this Betti side can be interpreted as a certain Fukaya category. So, but now if you kind of generalize in this bigger framework, then all right, so what's your Hitchin map, for example? In order to have Hitchin map, it's just projection to the support, to the spectral curve.
Right.
So you do have it.
Right.
Here. So at least you do have some ingredients. And whatever P filtration, whether it exists or not, but at least it's reasonable to ask the same whether it's this conjecture can be true, especially since you can speak about Borel-Moore cohomology of the stack. So then on the Fukaya side, you do have stack of objects, and you can take. You see, there are many technical details, like you want it kind of to work with semi-stables, and it's a little bit more difficult to say. Maybe you need to work with digistacks, but nevertheless, you do have Dolbeault, analog of Dolbeault and of Betti side. So then, and there is a very concrete example. In fact, there are two of them, and I think I spoke about this in this many years ago in this Fields conference where you also were present. Let's take, instead of the cotangent bundle to the curve, let's take C star square.
Okay.
Which is analog of this trigonometric analog of the cotangent bundle to C star.
Yeah.
It's a complex symplectic surface. And in this case, one can describe quite explicitly the Betti side. In fact, there are several descriptions of the Betti side. And also you can, it's just spectral curves in C star square. It's not a very difficult thing. So then it's rather the question about trigonometric analog of P equal W. And there is also, of course, the elliptic analog. In fact, there is not only one. you can take the product of the elliptic curve with C star with form which is a product of Calabi-Yau form on the elliptic curve and dz over z.
So in the C star cross C star case, are you insisting on projective support for the sheaves or not?
Well, there are. It's a bit longer story than I've just said, because in order to define these categories properly, you need to choose a compactification, which means that this C star square should be compactified to a toric surface. And this appears in the definition of both categories on the Dolbeault and on the Betti side.
Yeah.
Because your spectral curve should intersect nicely toric divisors and so on, so on. So I can tell it's a different story. I don't.
I've seen enough of this story to know.
Just to point out that this conventional Higgs, it's not everything which does exist, but for your generality, it's just another example in the list of Calabi-Yau categories. So that's why I like very much this general technique. So it's not a question, it's rather a comment, but I have questions.
No, I'm very grateful for the comment.
Yeah, I can, if you like, I can write you more.
Please, yeah.
Yeah. Now, but I have questions, which are questions and not comments. So first, we know that whatever whole algebra you take, like Coha or conventional, just 1/2 of some quantum group, whatever is it. So your BPS Lie algebra is a Lie algebra for this 1/2. Now,
yes.
How can you see geometrically the whole thing, or you just have to double Coha first and then?
No, I prefer to try to go at it geometrically. So there is a construction, and it looks a little bit, maybe a little bit odd, but it takes as its starting point a kind of recognition theorem of Borchert's for when an algebra is 1/2 of a Borchert's algebra, and it's I'm not going to do justice to this. It requires a form on each graded piece of your Lie algebra. So not a form that pairs it with the opposite piece, but an actual a form on satisfying certain positive definiteness properties or sign definiteness properties. In the I'm not going to do this justice. Yeah, in the case that you're looking at a cohomologically graded thing, which lives entirely in even cohomological degree, this corresponds to the sign definiteness of the form you get, the kind of polarization forms. So if you have a pure mixed Hodge structure and left Schertz operator L, you get just such a form on each cohomological piece, where you take two objects in the same cohomological piece, and let's say they both live in, in the lower half. You apply the left Schertz operator to one so that it lives in the mirror, and then you pair off with each other. So the starting point to get from algebra to geometry is to try to come up with some kind of modular left Schertz operators. So some divisor on all of your moduli spaces, which kind of respects the whole algebra structure, which kind of respects extensions. So over on the pre-projective algebra side, obviously things are a little bit made more subtle by the fact that these moduli spaces and moduli stacks, although they all have pure Tate type cohomology, they're not ever projective. The thing to try and find is a modular compactification of the pre-projected stack. So yeah, projected stacks that contain them that also have a kind of Hall algebra structure on their cohomology, or Hall algebra structure just on their points. And such a construction is in fact given by the construction of McGusty and Nevins, which they used to prove Cohen surjectivity for Nakajima quiver varieties. I mean, they really utilize this construction in the smooth case, but in fact, that construction becomes somewhat easier to work with in the singular case. So this gives you the ingredients to come up with a kind of geometric description of this this non-degenerate pairing on each graded piece of the BPSD algebra. Yeah, so that gives you a way to come up with a sort of geometric double.
Yeah, because this Borchardt recognition, it's just for his version of Katz-Moody, not for quantized. It's
yeah, that's true. So yeah, I'm just telling you how to geometrically double the BPSD algebra for
it would be nice. Yeah,
pre-projective algebras.
Since you mentioned Borchardt, yeah, I mean there is some activity on kind of deriving vertex algebra. In particular, I saw today one of Dominic's students, Latincev, posted.
Yeah.
Yeah.
I haven't had enough time to read that yet.
No, I haven't read it, but I knew that it would come because Adil Khan sent me some draft of his paper on virtual derived virtual classes, and he mentioned that. But anyway, this vertex algebra structure, if I remember, I think I heard Dominic's talk many years ago. It uses just the cohomology of the stack and nothing more. In particular, chief of vanishing cycles, it does not appear in his story. It seems to be not a three-dimensional, but there are some results that having a quiver with a potential, maybe specific quiver with specific potential, like the one which you mentioned, quiver for C cube, one vertex with 3 loops and cubic potential. You can construct some vertex algebras, new type vertex algebras. So my question is, I mean, from the perspective of this two-Calabi-Yau, because you can always produce 3 Calabi-Yau by multiplying by a line, whatever. Can you sort of see in this generality vertex algebras? C cube is a product of C square by C. This is exactly this story.
So let's see. The route I would take is the way to think of the coha for the triple quiver with potential, or one way to think of it, is as a factorization cosheaf on A1, or an algebra in the category of factorization cosheafs on A1. So if I have take an open subset of A1, I can restrict the stack. Sorry, let me take one step back. I look at the generalized eigenvalues of all of the extra loops.
So your A1 will be, say, direction of Z, or what?
Yeah, exactly.
And
so I have
at point you have 2 commuting or whatever.
Right. So for a general quiver, when I take the triple quiver with potential, I'm looking at the pre-projective algebra adjoined an extra commuting variable. I can't remember what I called it, Z maybe, Z. And there's a morphism from the stack of representations of that algebra to the stack of representations of, well,
tripled quiver with a potential.
no, just to the stack of representations of the one loop quiver. Just remember in fact, a morphism to sim of A1, given by just remembering the generalized eigenvalues of the extra loops.
Mm-hmm.
And this gives me a factorization cosheaf on A1 because, yeah, if I look at the stack of representations where the generalized eigenvalues are in this blob and this blob, it is the Cartesian product of the stack of representations where the generalized eigenvalues are in this blob with this blob, because the operator is central. So if for any representation of this Jacobi algebra, there is a canonical direct sum decomposition into eigenspaces for that extra operator. And that tells me that there is this Cartesian product description. And then Tom Sebastiani plus an extra piece of work tells you that the critical cohomology forms a factorization cosheaf once pushed down to sim n of A1.
Good. And basically then there is some general abstract nonsense that factorization cosheaf is the same as a vertex algebra, and you think it's exactly the same.
Right. And there's also some abstract nonsense saying that if you have a commutative algebra in the category of factorization cosheaves, it has to be generated on the small diagonal. And that's where the support lemma is really coming from. The proof for the claim that the BPS sheaf is supported on the locus where all of the generalized eigenvalues of the extra loops are the same is really the proof of the statement that algebra object in the category of factorization cosheaves is generated on the small diagonal.
Yeah, actually, I don't know, in this general story, which kind of many people, like probably Kevin Costello wrote it in detail in his book, which I haven't read. But anyway, is it possible to recognize what kind of vertex algebra do you get? It's a theoretical device, which you can just say that there is a vertex algebra structure, but you cannot compute it.
I think it would be. I think it would be interesting to try and work it out. I mean, somehow it's obvious what one must get, right? Because we know in type, we know that at least for the 0th piece of the BPSC algebra, we have a Kac-Moody algebra.
Yes.
So it's got to be the vertex algebra associated to a Kac-Moody algebra somehow. But
okay.
Maybe it's easy to prove this. And maybe it's also somehow easy to work out what happens to all of the non-zero cohomological stuff.
Some sort of Drinfeld-Sokolov type construction for this Kac-Moody algebra. Right. Okay, Okay, so it's an interesting idea, It's an interesting idea. Because so far, you see, what we can do is just to work with the torus localization, so to make things very concrete. And when you apply torus localization, then you have a particular basis and you can write down formulas. All right, so I don't know. I heard from this Adil Khan notes that there is a very general torus localization at the level of DG stacks, something which vast generalization of a TIA bot, and probably using that one can compute everything if such a theory exists. Because I asked people many times, kind of different experts in stacks, what's the localization for stacks, and in particular, you know, there is this Bielyanitsky-Berula, very helpful theorem for computing motifs or cohomology of varieties, but I don't know analog of it for stacks. Do you know?
No, not really. I don't even.
Classical, you have cis direction on the smooth variety, and it's a Morse, which means that everything decomposes into the union of cells.
Right.
Yeah,
but BB decompositions outside of smooth cases anyway have me worried. But then for vanishing cycles, there is this. Actually, one of them is due to yourself and Maxime. There's a sort of hyperbolic localization that one can do, right?
Yes. Okay. Yes.
This is, I suppose, one way of interpreting the integral identity in motivic and cohomological DT theory as a kind of hyperbolic localization.
Yeah, but it's sort of different. It's less generality than kind of, maybe not less, maybe it's sufficient for all examples, but at least it looks like it's not as general as I want. Yeah, but sort of.
But I mean, say you have a C star action at the kind of 2D level, then you fix it to be a C star weight 0 action at the 3D level by, I don't know, if your original action is scaling. Yeah, I mean, it can always be done. Yeah. And then use hyperbolic localization of vanishing cycles at the 3D level. And there you can use the fact that the ambient stack is smooth, whereas maybe after dimensional reduction, the stack is horribly singular. And so localization or BB type decompositions become more tricky.
Yeah. Okay. All right. And by the way, there are some work on the geometric construction of coha in the derived setting, and probably your construction covers everything, and you have a BPS algebras like Porta-Sala in the derived sense. They did it for.
Oh, yeah. Yeah, I mean, they're looking at a sort of categorified version of the 2D coha, right?
Yeah.
So one would, get the 2D coha out by just applying the Borel-Moore homology to what they produce. Yeah, I don't know. I'll speak to Francesca next week. Yeah, it's not clear. The question I ask Francesco every time I see him is whether there's some way of proving this nonabelian Hodge isomorphism in Borel-Moore homology using what they do. And I don't want to answer the question for him, but I think they're encouraged in the belief that there will be a way to prove some kind of nonabelian Hodge isomorphism at stacks using what they do. But I've not extracted that precise statement from that paper yet.
Yeah, by the way, this conventional non-abelian Hodge theory, due to Simpson, involves some intermediate objects. It's not just Dolbeault and Betti. There is some life between them, and this is. It does not appear neither in your story nor in the proofs of other people. I don't know this IP like Mauri or whoever.
Right. I mean, the conjecture is still just a conjecture.
Like harmonic bundles.
Yeah. Right. Yeah. I mean, I'm essentially proposing to piggyback off the classical non-abelian Hodge correspondence.
yeah, because you see, we have kind of, it looks like my son has already left. It's too late in France.
Oh wow, yeah.
We have, yeah, in UK too, but 1 hour early. We had some work with him, with Alexander and with Roma Fedorov on,
right.
Yeah, on these motives, and we have sort of conjectured. It's maybe have not written, but that these motivic classes which we compute, that they are sort of invariant with respect to the deformation on the twistor parameters. And when you see nonabelian Hodge theory, it's about twistor family,
right,
of varieties or of categories, if you categorify. And so we compute some motivic classes of Higgs bundles in different versions. And what we observe, but when we move from Dolbeault to the RAM, then these motivic classes do not change. Basically, the variety is different, of course. Algebraic structure and the complex structure is different.
Yeah.
The motif, for some reason, it survives. And so then we have some, yeah. So then it's a question that these missing structures in P equal W, maybe they can clarify why one filtration kind of transformed to another one, but maybe in a natural way along some flow. I don't know.
I don't know, one thing that one odd feature of the Donaldson-Thomas theory, let's just say of A2 or A3, is that these stacks, so the stack of commuting matrices, say, it doesn't have a affine paving in any sort of concrete sense. If you take, for example, the stack of pairs of a nilpotent, of a commuting nilpotent and general matrix, I think then you have a affine paving, but for just the whole stack, it doesn't have an affine paving, but it behaves in almost every respect as though it does, because it has pure Borel-Moore homology of tape type. So yeah, it looks, and you know, the way you calculate the motivic DT invariance via power structures and sort of, you know, like this from your paper, from power structures and sort of playing between the nilpotent and the full locus and the C-star locus, it looks like it's like an algebra of Tate motives. It's an algebra of so it looks like it's a kind of affine paving, but without there being an affine paving. On the P equals W conjecture, maybe in the end it comes down to the same thing, that once you really understand the Donaldson-Thomas theory of both sides and how to manipulate them, they end up having not a paving by tori, but behaving in all respects as though they do. Where on the Betti side, it's a paving by actual algebraic tori, and on the Higgs side, it's a paving by total spaces of canonical bundles of products of elliptic curves. So maybe you end up with just like some algebraic expression in those motives on both sides. And once you compare them, you have the same algebraic expression. You plug in on the one side complex tori, and on the other side total spaces of canonicals on products of elliptic curves, and you just get the, again, because of the stupid rank 1 calculation, P equals W. That's what.
Maybe on one side you have sort of a cluster varieties, which is computable, and on the other you have motifs of essentially elliptic. Okay, maybe, yeah, but
Yeah, maybe. Yeah.
maybe.
Yeah, that's an idea. That's an idea from very late in the day in the UK.
All right, so okay, last chance to ask Ben a question, because before the midnight will come in Edinburgh. Okay.
Actually, I still have a question waiting to get Jens' discussion here, and actually that answer.
For you, I would cut it off because I have a lot of stuff. Okay, go ahead.
Well, it's about the positive in the characteristic T case. You can see that the Betti sides, and which can be done over other things over finite field in terms of counting.
Mm-hmm.
And so I don't know if that's the first question is the static version of that. I know that you may not be interested, but did anybody ever ever discuss it about the static version of this decomposition theorem similar in terms of counting over finite field, assuming the variety was defined nicely over some algebraic fields?
Yeah, I'm not sure. I've not thought that through.
Yeah, it's kind of a question that most complex geometers won't consider.
Yeah, I mean, a lot of I should mention, just to give credit where it's due, that a lot of what we know and a lot of where the predictions come from on the Betti side, working over finite fields and actually counting points and
especially Hausel and
yeah, exactly, especially I'm thinking in particular the paper of Hausel and Rodriguez Villegas.
Yes.
Yeah, I mean, a lot of like the notion that there should be something like the integrality isomorphism on the Betti side comes from observing that one byproduct of their work is that the generating function of counting functions across all ranks forms a plathistic exponential, which is a kind of decategorification of taking the free symmetric algebra generated by something. So there's a lot of hints coming from that side of the story.
And also that on the double sides and most of the formulation, even including the Higgs bundle, is algebraically over other characteristics still makes perfect sense.
Right. And again, to give credit where it's due, on the Dolbeault side, there's okay, so the prediction that there should be a Lie algebra on the Dolbeault side, which becomes the BPSC algebra, is I think originally due to Olivier Schiffman and comes as a byproduct of his work on again counting Higgs bundles over finite
fields.
Yeah.
Okay, well, thank you very much. I know it's kind of late. I didn't know if you have your supper yet.
No, not yet.
Oh,
no, I've got a very nice curry waiting for me, so I'm excited. Yeah.
Well, thank you very much for giving a series of the lectures. It's very inspiring.
No problem. Yeah, and I noticed while I was going through that talk that there were a couple of typos in my slides, so I'll send them.
You can correct and send sort of.
Yeah.
All right, so I think we should let Ben to have his curry, whatever dinner it will be. Thank you very much for your lecture course. Very, very useful. And yeah, I'll write you about this C star square stuff. Okay, thank you very much.